previous lecture we studied the working and fabrication of a junction field effect transistor, and we continue the investigations. For any electronic device, one of the most important characteristics are current voltage characteristics of the device. So, we take IV characteristics for N type JFET. We will not spend time, we will not duplicate the studies by taking P type JFET, because they are identical except at few places, as I discussed in the previous lecture, that the gate source voltage will be positive in the P type junction field effect transistor, while it is negative in the case of N type JFET. So, the characteristics which we have already drawn, they were this. This is drain current and this is VDS in volts, and this is in normally milliamperes, and these are the characteristics. This was Vp, the pinch off voltage, and these are the characteristics for VGS equal to 0. This is -1 volt, -2 volt, -3 volt, and here these characteristics we will get, for example, for -4 volts. These IV characteristics, the drain characteristics of the junction field effect transistor, they can be divided into 3 different regions. One is this region, from here to here, this is ohmic region, From here to here, this is saturation region. And here, this is the where the drain current drops to 0, that is the cutoff region. So, the characteristics has 3 regions: ohmic region, saturation region. Saturation region is also called actually constant current region. Here current is almost constant, so also called constant current region. And third is cutoff region. These are the 3 regions. This region where the current starts saturating, before that the region is called ohmic region. So, first we take ohmic region. Ohmic region obviously is VDS values greater than 0 and less than VDS less than Vp. the pinch off voltage. And here we are seeing from the plot that current is varying from linearly with the change of VDS voltage. So, in this region VDS is small and it is below pinch off. So, there is no pinch off, no pinch off of the channel. There is no pinch off of the channel and the current increases. Now, when we increase the gate source voltage, then the resistance increases, the change is slope. You see, slope is changing, this is voltage, this is current. So, the slope gives, inverse of the slope gives the resistance. So, here the slope is changing, and this you understand that when we increase the gate source voltage, this gate source voltage, when we increase, this channel conductance falls, the resistance increases for the reasons which we have discussed, that by increasing negative potential on the gate, the depletion regions will spread more, making the channel narrower. So, pinch off does not occur, but the resistance varies on the gate source voltage. The resistance in the ohmic region varies from 100 ohms to almost 10 kilo ohms, and obviously this is a voltage controlled, it is a voltage controlled resistance. This voltage VGS, this is controlling the resistance. Here the slope is changing, and which is a function of VGS, and in this JFET, junction field effect transistor, can be used as a voltage controlled resistor. VCR, voltage controlled resistance, and so this is about the ohmic region, and then we go for saturation region. In the saturation region, and this saturation region starts from this point, and this point is actually VDS. The drain source voltage has to be higher than VGS minus the pinch off voltage. So, this line here, this is at the point VDS is greater or equal to VGS minus VP. This is what I have written here, that saturation region starts when DPS is equal or greater than this value. In this region, the drain current ID depends entirely on the gate source voltage. Drain current ID does not depend on drain source voltage VDS, but it is a function, drain current is a function of VGS, gate source voltage. Here this current is varying as we are changing the gate source voltage. It is constant with respect to change in VDS. These are almost horizontal lines. The drain current is not changing when we are varying the VDS in this constant current region, and that is why it is called a constant current region. Here the dependence of drain current on the gate source voltage has a nonlinear relationship, and this relationship can be expressed by a square law, and that is I d, the drain current, is equal to I d S S into 1 minus V G S by V P square. This is an important equation, and this gives the relationship between drain current I d is expressed in terms of gate source voltage by this equation, and from this we will use this equation very frequently. Now, very important thing, when the device is to be used, when a junction field effect transistor is to be used as a amplifying device to amplify signals, then JFET is operated in this region, in the saturation region it is operated, and this relationship, nonlinear relationship between Ig and VGS, gate source voltage dependence Id, this has this relationship as expressed by this equation is parabolic in nature. So, we can get actually the transfer curves, transfer characteristics of JFET. Why transfer? This is the drain current and this is the gate source. The two are they are not the part, for example, of the output current is ID, but this is a gate source voltage. So, transfer. So, the curve is a parabolic, this is ID and this is VGS, gate source voltage 0 positive, and here it is negative, and in this expression when VGS is 0, here the maximum current ID, here this is IDSS. Drain current when gate is shorted with the source, gate is shorted with the source, that means gate is at 0 potential, that is IDSS, and so this is that current, and as we are changing VGS more negative, drain current is falling and here it is off. So, this is the parabolic plot, and this value where this drain current drops to 0, this we call as VGS, gate source voltage off. These are the drain characteristics for the N type JFET. The curve will be in the opposite, because for a P type JFET the gate source voltage is positive. So, it will be this way. This is drain current and this is VGS and this is this, and this is the magnitude equal to this, which is also Vp, the pinch off voltage here. And so, from here, from this transfer curve, we get that the magnitude of Vp is the same as VGS off. What is VGS off? VGS off is that voltage, gate source voltage, which puts drain current to 0. And we can see from here, from this curve, when drain current is 0, then VGS off is equal this relationship we get right from this equation 1 by putting ID equal to 0. Then from here we get VGS, the magnitude of VGS off we will call, because that will put the drain current 0, and that will come out to be Vp. That is why I have written here Vp, or it is same as VGS off. Followed from this curve we are getting this plot, and if we plot changes in ID as a function of changes in the gate source voltage, then this is parabolic behavior, which is expressed by this equation. We also see here that VGS off makes ID 0, and that gives right from this equation Vp equal to VGS off. So, that equation 1 can also be written as ID IDSS VGS VGS off. We can write that equation, let us call this equation 2. Now, one thing is certain, that since in this equation IDSS represents the highest current in the JFET. So, these quantities here in the bracket, in this bracket, this has to be positive and less than 1. So, what I have said is this, that since IDSS represents maximum current for JFET, the quantities in the bracket, this has to be positive, and it has to be less than 1. Now, why I am saying this, that we can just substitute VGS for any voltage at which that gate source voltage at which we want to know the drain current for the device. We put the value of this VGS off or Vp, either we substitute this just numerical values of VGS and Vp can, and if we know the current, drain current when gate is shorted with the source, that current is known, then we can find out the amount of drain current with the any value of gate source voltage. And then So, this is all about the constant current region or saturation region. I repeat that the device is operated in this region when its purpose is to amplify the signal. We will see when we will develop the model for the FET, we will use the analysis and derive an expression for the voltage gain. Now, the cutoff region. Cutoff region is this region where the drain current is 0. So, for n FET, n JFET, VGS is less than Vp, that means more negative. VGS is less than Vp means is more negative than Vp, and in this case the drain current is 0. In this region drain current is 0 and the device is off. This region. In this region, this is in this particular case minus 4 volts and Vp was also 4 volts. This voltage is also 4 volts. VGS off is equal to Vp. This is what we have said above. And we say that for the cutoff region, VGS is to be lesser than Vp, that means more negative than Vp, magnitude of Vp has to be lesser than this. So, that will put the device into off. So, this is about the working and the IV characteristics of a junction field effect transistor. To make you familiar more about the device, let us take one or two examples, numerical problems on the device, and they will clarify some of the doubts which you might be having. So, example 1. This is for a N junction field effect transistor. The parameters of the device are that IDSS, when the gate is shorted with the source, that is the maximum current in the N junction field effect transistor, this is 8 milliampere, and Vp is minus 4 volts, minus 4 volts. Then find out the drain current. Number 1, when VGS is 0, B, when VGS is minus 2 volts, and C, when VGS is minus 4 volts. Under these 3 values, find out the value of drain current. This we can do simply with the help of that square law expression for the drain current in terms of the gate source voltage. So, ID is equal to IDSS 1 minus VGS by Vp. square. Now A VGS is 0. In that case ID comes out to be equal to IDSS when VGS is 0. This is the definition of the current IDSS, and this is given as 8 milliampere. So, this is 8 milliampere. Then for B ID is 8 milliamperes, that is the value of IDSS. I have substituted in that expression, and 1 minus, I said that either use both with proper sign or just substitute magnitudes, this is one and the same thing. So, if I take with proper sign, just this is minus 2 and this is minus 4 in this whole square. So, you see here this is the same if I have just substituted the magnitudes. So, just substituting magnitudes, so there is no confusion about sign, it is better just we talk in terms of magnitude. We have substituted the magnitude of VGS and VP also, and so this results in a current of 8 milliampere into 1 by 4, which is 2 milliampere. This is what is expected when we increase the gate source voltage to minus 2 volts, the current will decrease from its value IDSS. IDSS was 8 milliampere and this is 2 milliampere. And then C, when VGS is equal to minus 4 volts, then ID will be 8 milliamperes by 1 minus, I am just substituting the magnitude 4 and Vp is also 4, this is square, and that makes ID equal to 0. That is expected also because of the plots. If you remember, here ID is 0 when VGS off, which is minus 4 volts, and Vp is also 4 volts. When I have substituted anyway the given values, then ID is 0. So, at 3 different gate source voltages, we have calculated the drain current with the help of this expression. This is a example 2. Again a n JFET which has IDSS as 10 milliamperes and Vp, the pinch off voltage, as minus 5 volts. Then we have to find out VDS, the minimum value of drain source voltage, minimum value of drain source voltage for pinch off when VGS is equal to minus 1 volt. I repeat, a n type junction field effect transistor which has the maximum current, the IDSS, as 10 milliampere, the pinch off voltage of minus 5 volts, and we have to find out the minimum value of VDS for pinch off at minus Vp. So, now the solution, you remember we have written VDS minimum is equal to VGS minus Vp, and so this can be easily found out. This is given as minus 1 volt and this is given as minus 5 volts. So, this is 4 volts. In this, under this condition, a drain source voltage of 4 volts will pinch off the channel, and if we have to find out the drain current here at the pinch off, then the drain current again we can find out IDSS 1 minus VGS by Vp square, and this we can find out 10 milliamperes 1 minus 1 by 5 square. When we solve it, it comes out to be 6.4 milliampere. This way the problems can be handled. So, this is about junction field effect transistor. We will return to junction field transistor again, and when we talk of biasing and other things, let us talk of other devices. The next device in this module, which is very significant, most important device today in electronics, is MOSFET. In the beginning, I have said that MOSFET stands for metal oxide semiconductor field effect transistor. This is MOSFET. Sometimes in the interview it is asked, elaborate for what MOS stands in MOSFET. So, you should know metal oxide semiconductor. As the name suggests, here the gate, this is very important and a basic difference, and that gives all the differences. The basic difference between a junction field effect transistor and a MOSFET is that here gate is separated by a insulating layer, oxide layer. If we are talking of silicon, then a thin layer, by thin I mean for example 50 angstroms thin, then this is oxide layer separates the semiconductor with the gate electrode. So, gate is separated from the semiconductor by an insulating layer, and as I said that insulating layer, when we are talking of normally the silicon is used. So, silicon oxide or silicon dioxide is the layer which is used, and that is one reason that why this MOSFET is also sometimes called insulated gate, insulated gate MOSFET, FET, insulated gate FET. We will see that there are two types of construction, and that means how through the field induced from the gate through the insulating layer, how the conductance of the channel is affected. The whole working depends on that, and there are two kinds of MOSFETs. One is depletion MOSFET. Depletion MOSFET. often written as D MOSFET, D for depletion, depletion MOSFET. And second one, enhancement, enhancement MOSFET, or simply E MOSFET. There is an insulating layer which separates the gate from the semiconductor. I will give you the construction, but there are two possibilities. One is the depletion MOSFET, that is D MOSFET, and other is enhancement MOSFET, that is E MOSFET. Both are very widely used, and first we take the depletion MOSFET. Depletion MOSFET. First, the construction, fabrication. Here is a small crystal of say p type silicon, which is a substrate. On that we generate two heavily doped N regions, N plus, N plus, and then let me first complete the drawing and then we will talk. This is the insulating layer, SiO2 layer. It is very thin, say 50 to 100 angstroms thick, very thin layer. How it is achieved? That this silicon on which we are making the device, a fresh pure oxygen, this is kept at a temperature and that flows. It is all computer controlled. So, how thin oxygen oxide layer we need, that is controlled, and hence a oxide layer is obtained. Then two windows are obtained by etching, that means from the two regions here and here the oxide layer is etched and metal electrodes are put, and one electrode, these electrodes normally are of aluminum, and one electrode is put here, and before all this is done a channel is implanted here. This is N channel, N channel which is implanted, and these are the three electrodes. This is source, this is gate, and this is drain. These are, let me do like this, these are metal electrodes. This is a depletion MOSFET. I repeat all what I have done, that p type silicon is taken as substrate over which two regions are created by heavily N type doping, and in between this N channel is implanted. These are sophisticated techniques of creating N or p type regions at specified places, very precisely, because this dimension I will draw still bigger to make my points clear, but actually these dimensions is a fraction of a millimeter. The total dimension is a very small 1/100th of a millimeter or still smaller. So, the channel is implanted and oxide layer is put, so that the gate and the semiconductor, they are separated by this oxide layer. This I will, to put my points clear, I will make a bigger figure, but let me point out one big difference with JFET. In JFET, in the N type, the gate voltage was negative necessarily through reverse bias the junction. Here below the gate there is no PN junction. Therefore, the gate source voltage VGS can be, it is very significant point, can be 0 or positive voltage or negative voltage, all possibilities. We can give gate positive potential with respect to source, or we can keep it at a negative potential. So, positive, negative or 0 potential, all are possible in this device. It is a big difference. Why we do not operate a field effect, a junction field effect transistor with a, this was a FET, this is of course P type, but it is all right. So, here now to forward bias it, we will have to give a positive potential, positive potential will forward bias the PN junction, lot of current will flow. So, that will not be operative. That is for N type JFET. The figure must be, yeah, here. This is gate, this was P type material, this is N, and we have said that gate in the N type JFET is always operated with the negative voltage, and we draw the characteristics where the gate source voltage is negative, more negative, more negative, and so on, because making it positive will make the junction forward bias, lot of currents will flow and a different phenomena will occur and will create problems. In this case, in the MOSFET, there is no direct, there is no PN junction, hence it permits the voltage at the gate with respect to source either positive or negative or 0. Now, now let me redraw this figure and show you that how the charges induced through this dielectric layer will change the conductance of the channel and hence will control the current. I will make a bigger figure and this is oxide and here is the gate electrode, and this is the semiconductor which is P silicon and here is the body B, which is shorted to internally shorted to the source. And we apply a positive voltage here between drain, this is drain, this is source, and this is gate, and we apply to the gate. For example, we start with a negative voltage, this is VDD and this is VGS. Now, let us see how the channel is N type. The channel is N type, this is N region, this is N region, heavily doped, and heavily doped is represented by plus sign, is still more heavily, and 2 plus signs, this is heavier than this doped. So, how the field will induce and the depletion region it will create. For that, let me just draw this portion much larger. This is the that SiO2 layer, and these are the electrodes. This is heavily doped N type, this is source, this is drain, and this is gate. Now, when we apply a negative voltage to the gate, then these, look at these charges, this is negative charge and this is N type channel, N channel, and so here are the electrons, this is the SiO2 layer, SiO2 layer, a dielectric. Dielectric, this field at the gate, very important, the field at the gate will polarize this SiO2, L will induce a positive and negative charges, they are bound charges in the insulating, it is SiO2 is insulator, there are no free charges. So, the field at the gate will induce the opposite charges. This is, you must have studied how the capacitance of a capacitor is increased by introducing a dielectric. Dielectric get polarized and that nullifies there, in the case of a capacitor, nullifies some charges of the plate. So, the capacitance increases. In this case, this will induce some positive charges here, this negative just at the surface, just above the channel, these positive charges will be induced, and these induced positive charges will recombine with some of the electrons. So, therefore, in this region this is the channel. Now, this is the depletion region which will occur, and this is of course the oxide, and this is the gate negatively charged. I think I have made amply clear what will happen. Look here, that this is the geometry we are talking. The gate I am taking negative with respect to source, and this negative field at the gate through the dielectric will induce some positive charges in the channel region. Channel was N type, that means negative charges, the electrons were there. Now, these induced positive charges will recombine with some of the electrons and a depletion region will be formed, and hence this depletion region is always a region devoid of mobile charges, that means high resistivity region. So, by this depletion region will increase the resistance, will decrease the conductance of the channel. If now we keep this constant, there will be a current in that these will be the characteristics here. This is VDS volts, this is ID. When there is, if there is this voltage, gate source voltage is kept 0, then this is the channel. When we change this voltage VDD, that is VDS, we change between source and drain, the current will flow because of these electrons. This is N channel, current will flow. So, this current will be this, and now this is VGS equal to 0. Now, we have given a negative voltage that reduces the conductance. So, for the same voltage, same drain source voltage, the current will fall, and this way we will get these characteristics. This is at VGS of minus 1 volt, minus 2 volt, minus 3 volt, and so on, and a voltage may come where this channel may be completely, the depletion region has completely taken over and there is no continuity, there is no conductance between drain and source. So, here the device is off. This is the depletion mode for the device. Now, if I give a positive voltage, if you have followed this, that negative voltage induces a depletion region, because positive charges will be induced in the channel and that will take some of the negative charges of the channel, mobile charges of the channel, and hence the conductance will fall. If we give a positive voltage to the gate, which is possible, and that will enhance the conductivity, that will induce more negative charges in the channel and hence the conductance will increase. So, the currents will change, and here this is plus 1 volt VGS, plus 1 volt, plus 2 volts, and so on, and this is known as depletion mode is now working in a enhancement mode. Enhancement mode. Remember, enhancement mode is different than enhance E-type MOSFET. A depletion MOSFET can be operated in the two modes, depletion mode or enhancement mode, simply by changing the nature of polarity at the gate. If gate is negative with respect to source and keep on increasing that negativity, current will fall, because depletion region will penetrate more and more in that channel region, and by giving a positive voltage, more charges, negative charges will be induced by the field in the channel region and the conductance will increase. So, for the same voltage, more and more current will appear here. This is higher than this and this is higher than this. So, these are the characteristics of a depletion MOSFET, drain characteristics of D MOSFET. We will continue our discussion on MOSFETs.